Concentrations and dilutions. So we are going to be looking at solutions. So part of what we need to do is to have some vocabulary. So a solution is something in which I'm mixing two things together. And the concentration is how much stuff is in that certain volume, the stuff being the stuff that I'm putting into my solution. So solution is a mixture, but it's a special mixture in that we're assuming that it's a homogeneous mixture. So we assume that the mixture is homogeneous. Again, what that means is that it is a uniform distribution. It doesn't matter where I'm taking my sample from. I will have the same combination of solute and solvent. Solute is what is being dissolved, and it's a little weird because it's what I have less of. Solvent is what is doing the dissolving, and it's what I have more of. Now, clearly you could get to a situation in which you're adding so much solute, like so much salt to the water that I have more salt than water. We tend to not look at those crazy situations, those ones that are at the extreme ends, because those just aren't very useful. So we look at the ones in which my solute is usually diluted, meaning I don't have as much of it, because then I can actually do certain things with it and I don't have to worry about just extra variables that are going on. Which brings me to the next set of definitions. These ones are very qualitative. So dilute just means I don't have much solute, and it's a very qualitative thing because what might be dilute to some person may be concentrated to another. For example, if I put a little bit of a substance into water, you'd say, oh, that's dilute. Unless I said it was poison, then you'd be like, whoa, that's a really high concentration of poison. Concentrated just means a lot of solute. Again, it's qualitative. It depends on how much. So unsaturated and saturated is much more quantitative. So unsaturated means that I can still dissolve more solute into my solution. I add a bit of sugar into my tea. I could add far more sugar into it. It's an unsaturated solution. Saturated means I can't dissolve any more solute. And you can tell that because if you add more solute, that solute just stays at the bottom of your container. So if I actually got to a saturated solution where I had so much sugar in my tea that it was saturated, if I added more sugar to it, it would simply stay at the bottom of my tea. That's something that many of you may have seen if you have iced tea, right? So iced tea is notorious for not being able to dissolve sugar into it, which is why you shouldn't drink sugary iced tea to begin with. But anyway, if you add too much sugar into it, it just stays at the bottom of your glass, and it doesn't matter how much sugar you put into it, your beverage is not going to get any sweeter, at least not the solution part of it. You may be drinking the sugar residue at the bottom, but that's not your solution. So because these are qualitative terms, and this is quantitative, you can have them in any combination. I can have a solution that is dilute but saturated. So if something doesn't dissolve very well, I'm not going to be able to get much into that solution, like your iced tea. But it could be dilute in that it doesn't taste very sugary at all. Or I could have a concentrated solution that's still unsaturated. I could give you a glass of water that's incredibly salty. It's very concentrated, but I could still add some more salt into it. I haven't reached the limit of the solubility. And I can always dilute something by adding more solvent, right? So if something's too strong, I just add more, like, oh, I gave you tea that was too strong, I can just add more water to it. Concentration units. There are two major concentration units that we use in this class. The first one is called molarity, and that has a big M. And the second one is molality with a little m, and sometimes that little m is italicized. I understand that molarity and molality are two very close terms, and big M and small m are also, but I didn't get to vote on it, so we just have to deal with it. So molarity is what we usually use with reactions. So if I'm putting it into some sort of reaction, or if you had the magnesium and hydrochloric acid, we talked about a 6 molar solution. So molarity is where I look at the number of moles of solute that I have in the liters of my total solution. I call this ice cubes first. So the analogy is my ice cubes are my solute, and I have my glass, and I put my ice cubes in first, and I fill up water all the way up to the top. That would be my molar solution. Molality is where I take moles of solute and I put it in 1 kilogram of solvent. So it's per kilogram of solvent. I'm not looking at the solution. This is looking at how this is keeping solvent the same, but changing the amount of solute that I have. So this is ice cubes last. What I do is I fill up my glass completely up with water, and then I add ice cubes into it. The amount of water that I have in there stays constant. It's the amount of solute. So again, let me go over this. A molar solution. The way that we make it is that we have a specific flask that has a 1 liter marking. That's all it has. I'll show it to you in class. But you put in, say I want to make a 3 molar solution. So what I would do is I would measure out 3 moles of my solute into the flask. And then I'd add enough distilled water up to the 1 liter mark. And then I'd shake, 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 shake until it's really, really well mixed. That's a 3 molar solution. If I wanted to make an 18 molar solution of the same thing, I'd add in more moles of solute, add enough distilled water to the 1 liter mark, and then shake, 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 shake. So both of those solutions have the same total volume of solution, but because the 18 molar solution has more moles of solute, I don't have as much distilled water that I add to it. So the variable is the amount of solvent that I put into it. A molal solution would be different. In a molal solution, a 3 molal solution, I would fill the volumetric flask up to the 1 liter mark, and then add 3 moles of my solute in, shake, 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 shake. 18 molal solution, I'd fill the volumetric flask up to the 1 liter mark, add 18 moles of my solute, shake, 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 shake. The two solutions would be similar in that they would both have 1 kilogram, 1 liter of my distilled water, but they would differ in the amount of solution that I had. The 3 molal solution would have a less total volume of solution, and the 18 molal solution would have a larger volume. So again, ice cubes last. If I'm adding the solute in last, how much water spills over is going to depend on how many ice cubes I'm trying to cram into my glass. Solubility is a measure of how much maximum solute can be dissolved. What's the threshold limit? And I can look at that in terms of grams per liter, moles per liter, percent, that type of thing. So solubility is something that we'll be addressing quantitatively later on as when I'm looking at just a solution, what is the solubility of that solution? When we're talking about reactions, we'll be usually using molarity. Molality is for our next unit when we look at how a solution behaves differently than the pure solvent. You can be asked to do dilution problems. So the whole concept of dilution is that if I add solvent, I don't have as concentrated a solution. So the example I have here is if I start out with a cup of coffee and I add a cup of water. So now here's my coffee where it was, and I added the same volume of water. So now my total volume, I have 1 part coffee, 1 part water. So now my coffee is at its half of its original concentration. Coffee is now going to be half as strong. This is what happens when you put coffee concentrate or soda concentrate into water. It's a concentrated thing meant to be diluted, and they'll tell you how much it needs to be diluted. So one way to think about this is if I have 1 part coffee and 1 part water, then it's a 1-to-1 ratio. My coffee is now half as strong. The way that it's half is that I have my 1 part coffee in 2 total parts, right? So my 2 total parts are 1 part coffee and my 1 part water. So now I only have that 1 part of coffee in 2 total parts is half as strong. So try, what would your dilution be if I put 1 cup of coffee and I added 3 cups of water to it? How much of the coffee has been diluted? In other words, what's the amount of the original strength? So pause the video here and try that. So you're back. Hopefully you got the answer 1/4. So you can either look at it as a ratio. I have 1 part coffee to 3 parts water, or it's 1/4 because I have 1 part coffee to 4 parts total. So 1 to 3 ratio of parts means that it's 1/4 diluted. If that's tough for you to see, then always translate it back to that 1 part to the total, because that's really what a fraction is, right? The parts to the total. Another example using the math that we have is if I have a 3 molar solution that needs to be diluted to 1/3 of the original concentration, how many parts of 3 molar solution and how many parts of water am I going to be needed? And if I want to have a total of 600 milliliters, how much volume of each do I need? So the first part, if I want to do a 1/3 dilution, I need to do 1 to 2 ratio. So if you're doing a 1/3 dilution, I need to have 1 to 2. So 1 part of my 3 molar solution, what I'm trying to dilute, that's like the coffee, to 2 parts of water. Or another way of thinking about it is 1 part of my 3 molar solution to a total of 3 parts of water and 3 molar. I keep that ratio for a total solution of 600, right? So I want to keep a 1 to 2 ratio, and the total volume has to equal 600. So each part will have to have 200 milliliters. So 200 milliliters of my 3 molar solution to 400 milliliters of water. This is still a 1 to 2 ratio, or if I look at it in the parts to whole, it's 200 milliliters within a total solution of 600. So I'd start out with 200 milliliters and I'd add 400 milliliters of water till I got to the total solution of 600 milliliters. And then of course shake, 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 so it's completely mixed. Another way of doing this is serial dilution, and this is a way of being able to get very precise concentrations that are very much diluted from the original concentration. And we always think in practical terms, right? I'm doing this in a laboratory, and in our laboratory, we have the smallest graduated cylinder is 10 milliliters, and the largest one that's comfortable to use is about 100 milliliters. So I always try and work in volumes that honor that practical aspect of what I have. So if I have a solution, and this is what happens, is that I have a stock solution of 18 molar, and you'd be like, who makes a stock solution of 18 molar? The chemical companies do. Sulfuric acid comes as stock solution as an 18 molar stock solution. If I want to use that in a lab safely as a 1 molar stock solution, I have to dilute it. But I'm not going to take this big jug of 18 molars sulfuric acid and try and pour out any reasonable amount to it and then just add a whole bunch of water to it. That's not safe. It's also not very precise. So I'm going to do what's called a serial dilution. So I'm going to do a serial dilution. So I always start from the end. I work backwards. If I want to have 100 milliliters of a 1 molar stock solution, and I do this by literally counting up the number of stations that I have to have and saying, all right, if I have 20 stations and each one has to have 2 milliliters, well, people are going to make mistakes, they're going to flub up, so I'm just going to make 100 milliliters. So I always make a little bit more than we actually need, but not so much that I have to worry about storing it. So 100 milliliters of a 1 molar solution. I first figure out how many dilutions I want to make. So in this case, I'm doing 3 steps. I'm first diluting my 18 molar to a 6 molar. That's easier and safer to handle. Then I'm diluting that to a 2 molar solution, and then that to a 1 molar solution. The nice thing about doing it this way is that once I've used my 18 molar solution, I can just simply put that away, put it back into the acid cabinet. Because this part I have to do in the hood, and it's really hard and bulky to do things in the hood, in addition to having a super concentrated acidic solution. So I try and limit my contact as much as possible. So I start backwards. I say I need 100 milliliters total. So if I'm doing a 2 molar to a 1 molar dilution, that means that I need a 1-to-1 dilution. So I'm going to need 50 milliliters of my 2 molar solution diluted with 50 milliliters of distilled water. Right? So if I'm going from a 2 molar solution to a 1 molar solution, and I need 100 milliliters of that, half of it has to be this solution right here, and half of it has to be the diluted with water. In order to get the 50 milliliters of the 2 molar solution, having diluted it from the 6 molar solution, I'm going to have to make at least 50 milliliters of my 2 molar solution. I always choose easy numbers, right? So if I realize from a 6 molar to a 2 molar dilution, it's a 1/3 dilution, I'm going to choose a total volume that's divisible by 3 because I don't want my brain to do too much work. Plus, I don't want to have to read my graduated cylinder like to a third marking. Make it easy, make it precise. So 50 milliliters, the closest thing that's easy, that's close, that's divisible by 3 is 60 milliliters. So I'll make 60 milliliters of my 2 molar solution. To make 60 milliliters of a 2 molar solution from my 6 molar solution, I have to do a 1/3 dilution, which means I need 1 part of my 6 molar solution to 2 parts water. So it's got to be 20 milliliters of my 6 molar solution dissolved in 40 milliliters of water. Shake, shake, shake. Yes. In order to get that 20 milliliters of my 6 molar solution from this, I'm doing a 1/3 dilution. Again, I'm going to err on the side of doing a little bit easier. I'm going to make 30 milliliters of this. So it will require 10 milliliters, which I can deal with, of my 18 molar solution with 20 milliliters of water. 10 milliliters is easy to dispense. Now, I could do that with a pipette if I needed to. So 10 milliliters of my 18 molar and 20 milliliters of my water. So again, I'm working backwards. I figure out how much I need of my last bit, and then I work backwards and say, all right, I had to dilute this solution by half to get 100 milliliters. That means I need at least 50 milliliters of this. In order to make 50 milliliters of this, 1/3 dilution, choose an easy number. I'll make 60 milliliters of my 2 molar solution. Just use 50 milliliters of it, right? And then work backwards. So work out the dilution steps first, and then work backwards using easy numbers. And this is literally what we do in the lab all the time when I'm making up solutions for you. All my solutions come in stock solutions if they don't come in powders. All my acids do. And they come in weird numbers. I don't know why. Sulfuric acid stock solution is 18 molar. Sulfuric nitric acid comes in 15 molar. Hydrochloric acid comes in 12 molar. You'd think that they do like 10 molar for each of them to make life easy for us, but they don't. So I think they're just trying to make us use our brain a little bit. That's how you do serial dilution.